Welcome back. If you're new here, SEM TECH is an open source, closed loop, environmentally friendly mining and refining technology. And we believe it can be economically competitive with any method that we're aware of because the efficiencies are insane. So today I'm going to break down what SEM TECH is in plain language, the continuous mining unit, also known as the CMU, the continuous refining unit, also known as the CRU, a real life example of a 50-pound sample that we recently processed and showing you XRF results, and why we're open sourcing a lot of this. So stay tuned. SEM TECH stands for Saltwater Technology. The idea is simple. We use saltwater and electricity to extract and refine materials. CMU configuration, specifically, we're using hydrochloric acid that is produced using membrane electrolysis of salt water. Additionally, we use sodium chlorate, which is also produced from salt water and electrolysis. However, instead of shipping expensive reagents and constantly making waste, the whole goal is to generate what we need, run the loop, and extract the metals and keep going. With the chlorine-based CMU configuration, SEM TECH can digest and extract almost the entire periodic table. Acid plus oxidizing potential is strong enough to extract all precious metals, including iridium, rhodium, platinum, gold, palladium, silver, osmium, ruthenium, and much more. Rhenium, I can go on and on and on. 25 updated critical mineral lists by the United States government, SEM TECH can extract in one single step and in one leaching solution all but 7 of the 60 critical minerals. 4 of those critical listed minerals are barite, fluorspar, metallurgical coal, and graphite. Because they're raw minerals or components dug directly from the ground, they're not something you leach or digest into a solution in the same way. But even then, we can still create fluorspar, for example, synthetically by recombining the fluorine and calcium produced by our electrolysis system, creating much higher grade, much more pure fluorspar, just as an example. And the 3 remaining elements, silicon, titanium, and tungsten, can be extracted by using a different leaching solution, but still utilizing the same components and electrodes and membranes and everything. So again, we're talking about all precious metals, all rare earth elements, all toxic heavy metals, and with nearly 99% recovery rates. Additionally, lithium, rubidium, cesium can also be extracted alongside the rest of the alkali metals. It just requires a extra add-on electrolysis cell, but it'll be configured within the CMU and the same chlorine-based leaching solution. So very big part of the periodic table can be extracted. Here's something that people outside of the chemistry world might not realize. In a lot of traditional extraction, the target metal has very low recovery rates. 50% is considered normal and 80% is very good and limited to controlled lab environments. Because that SEM TECH is closed loop, we don't have waste streams where the minerals can get lost. And because of the strong oxidizing redox capabilities, elements like tin and selenium can't rob the gold in the same way that traditional leaching systems do. And this does not stop at raw ore. We can extract from mining tailings, waste, e-waste, batteries, solar panels, you name it. There's a lot of additional processes that this technology can be utilized in order to recover the remaining materials, remove toxic heavy metals, and neutralize the solution or material for safer disposal or usage into the environment. In fact, in our testing, the treated output can be safer than farmland soil because we've removed the mercury, lead, arsenic, and other toxic commonly found in rock and nature. In one client's example, they tried various filtration, treatments, even reverse osmosis, and just had issues. And this was a solution that they were trying to process. But running this clear solution liquid through our electrolysis system, it was a divided electrolysis system, we crashed out the dissolved metals and into a precipitate powder. And we have XRF results also of this precipitate powder showing the heavy metals like lead were plated off. So now with this electrolyte solution, it can simply be filtered and you get clean water. Far below EPA standards as shown in our results. And the part that will get everyone's attention is the cost. It only costed a couple dollars to electrolyze 1 ton of this liquid. Less than $5 and only 10 to 20 minutes. So the key thing that makes this all work is the ion exchange membrane. So what is an ion exchange membrane? In simple terms, they let us control the entropy of chemistry. So what mixes with what and when, splitting apart things, so forth, so that we could keep the system stable and continuously regenerating. In one quick example, sodium chloride can be electrolyzed through an ion exchange membrane to have chloride, the chlorine part of the sodium chloride, which is salt, the chlorine be attracted towards the positive electrode, while the sodium part of the sodium chloride, again salt, is attracted towards the negative electrode. This produces sodium hydroxide and hydrochloric acid. The membrane allows those two components to stay separated. Ion exchange membranes can be used in systems like redox flow batteries and other salinity, gradient power concepts, fuel cells, etc. There's a lot of magic you can do when you can control ion flow and separation. Literally, you can make electricity directly from salt water and fresh water mixing like at a river to an ocean, and there are companies that are doing so, utilizing these ion exchange membranes. But here's the issue, and historical blocker is the cost. Membranes are very well studied, plenty of scientific literature, but the membranes themselves have been always enormously expensive. From China, they cost hundreds of dollars per square foot. However, we developed a recipe that's a few dollars per square yard or meter. Few dollars. With superior electrical conductivity and better resistance to fouling as required in our harsh mining conditions. And that's why this matters. Nobody wanted to expose these delicate, overpriced membranes to mining waste. Our work is about making that practical. Now let's break down the CMU. We use a cation exchange membrane to regenerate the acids on the positive side for leaching while plating off the metals on the negative side. So here's the cycle. On the positive side, we use graphite electrodes to regenerate the solution, the leaching solution, to flow back into the leaching tank. In here we have our leaching material, or e-waste, whatever it is. The solution will oxidize and digest the metals into a water-soluble state within 10 to 20 minutes. This leach solution is pumped into the negative side of the electrolysis cell, which allows the metals to plate off. The plated off metals settle and collect at the bottom, where a valve simply taps it off like a spigot. The depleted solution then gets flowed back into the positive side to repeat the cycle, regenerating the acid and continuing the process. One of the simplest visual proofs that the system works is that it's capable of bleaching a pH strip. What that means is turning the pH strip white in acidic conditions. This bleaching behavior is very important because it demonstrates that the oxidizing redox potential is capable of dissolving the very strong noble metals. A very similar chemistry property is utilized when extracting platinum group metals from catalytic converters. So a lot of people utilizing hydrochloric acid and bleach. This isn't fancy chemistry. This is people doing it in their backyard. This is very well established, very well known. But we're applying it at a much stronger redox flow potential. Here's the key idea to understand. Electrochemistry, or electrolysis, creates extremely strong oxidizing and acidic conditions because chemistry is all fundamentally driven by electrochemical voltage potentials. You can think of it that we're not just adding chemicals to do the work, to do the chemical reactions. you're driving the reaction at the level where chemistry fundamentally happens, using electricity to do the work directly. Based off real-life test results with a crude, unoptimized system, the stated cost to extract a ton of ore is only $50 to $400 a ton in electricity. This is a much more generous estimate than what actually goes on, with a lot of margin for errors. But what's importantly is that the feed input is raw crushed ore, not even ball milled. Hammer milled is sufficient for leaching. Output wise, we're aiming for a concentrate of heavy metal powders and clean ore silt, as previously stated, safe for agricultural use. Everything so far stated is in regards to the CMU. Now the CRU, the continuous refining unit, is where we refine the concentrate powder produced by the CMU. We use the same exact electrolysis cells, same exact electrodes, membranes. The primary difference is the solution. For the CRU, we use acetic and nitric acid to separate the concentrated heavy metal powder, pulling base metals away from the precious metals. This can reduce processing costs compared to traditional chemical refinement or fire assays by 50 to 200 times and do it all in one single step continuously. In a single step, the metal powder from the CMU can be separated from iron, lead, and other base metals, leaving behind the gold, platinum, rhodium, and so on. Now, for this step, using acetic and nitric acid, silver and palladium will also dissolve and separate with the base metals. However, if you change the solution, you can selectively dissolve different groups of metals to refine it as you desire, as your feedstock requires. But the point is you're utilizing this electrochemical process to concentrate and refine out completely continuously. When I say there's no competition to technologies like this, it's not bragging, it's to stress the importance of needing to integrate this into the industry as soon as possible. Because many existing mining methods produce enormous waste. Even something as simple as a shaker table can leave water with dissolved or suspended lead, arsenic, and other heavy metals. Efficiency and selectivity are major limitations in the real world, plus the timeline problem. For example, cyanide leaching can take months. We do it all in 10 to 20 minutes. Unlike traditional processes, SEM TECH produces concentrated powders that retains a broad elemental range from the ore. A client mine out west sent a 50-pound sample of ore to be refined and processed through our system. That 50-pound sample was previously analyzed to contain numerous precious metals. And on the XRF on the powder, we demonstrated our technology capable of extracting the gold, platinum, and silver identified in the material. Iridium is an issue with being measured in XRF, and rhodium detection limits are very high on our specific XRF, as we utilize a rhodium X-ray tube for it. But in the XRF results you're seeing right now, you're seeing multiple rare earth elements, yttrium, ytterbium, europium, thulium, and others, supporting the broad elemental range claim. We also see zirconium, which surprised me, and titanium, though that could be due to the titanium electrodes that we're utilizing. But the point is that the technology works. The diversity and solubility is enormous. Tin, selenium, these traditional metals that traditionally cause lots of issues and headaches with miners. All of that just gets dissolved and plated off with our metal. It gets eaten with the gold. It gets all of it. That's why this technology works. I believe SEM TECH is just a start. That integrating this could create entire new industries utilizing ion exchange membrane electrolysis, or already completely revolutionizing and changing existing industries by increasing efficiencies, recovery yields, and so much more. That's why we're open sourcing this technology publicly. While the membranes are not released yet, we still want to finish some research and be in a position where we can actually manufacture and sell the units ourselves. We are currently seeking grants in order to finish that. But again, if there's anyone that's interested in helping out, please reach out. Otherwise, again, we have all the instructions, all the details on how to build these electrolysis units. And there's nothing stopping you from doing it yourself. If you want, you can spend millions of dollars in research and time and years of development, and I'm more than welcome to have people. And this is going to revolutionize the industry. There needs to be more people involved. There needs to be more people that are doing this. If not, again, please, we're trying to reach out and trying to get more proper equipment, proper laboratories, proper facilities, proper people, this is a project and I'm trying to do everything myself and I can't. So please, 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 if there's anyone interested, please reach out. I'll put down my contact information on the screen. Thank you for watching. Stay tuned. I'll be uploading a lot more.